Okay. So what I would like to do now is get back to dynamic programming. Um, and I think I'm going to suspend the problem of the day for a few minutes um, to try to just review a little bit a simple aspects of dynamic programming. And then I want us to go back to that once we have this kind of reviewed a little bit. Um, Last class, people should have seen how you implement a dynamic programming algorithm. Basically, what was the idea? The idea is we came up with a recurrence relation we cared about. Maybe it was the Fibonacci numbers. Maybe it was the binomial coefficients. Maybe, as we will see, it is more an algorithmic idea. Okay, in fact, I guess we saw that with our shortest path with K hops thing. And we then implemented this recurrence relation. Instead of making a recursive program, we used a table to store all possible intermediate solutions. This is a great thing if we have a recurrence that is going to make exactly the same call over and over again. Then we are better off storing the solutions. That is the dynamic programming idea. Were there any questions from last time about how the binomial coefficients thing worked, or any questions about backtracking about dynamic programming before I go any further? Okay, so let me review a very, very simple, again, what is the idea in a dynamic programming algorithm? Okay, the basic story is you're going to start you're going to formulate your algorithm as a recurrence relation or a recursive algorithm. You're then going to show the number of different instances, meaning input arguments to your recurrence, is not exponential, but is small enough that you could store every one of these problem instances, typically a subrange of the input, okay, in a table. And then you're going to specify an order to fill in this table. So the items that you need are always there when you want them. That is the three things that make dynamic programming work. One reason that one reason why dynamic programming I think people find tricky is because there's kind of a couple different things you have to keep in your head at the same time. You have to separate the problem of formulating the recurrence from actually implementing this thing. But if you understood the if you understood the problem of if you understood the problem from last time about how we implemented the binomial coefficients, you will be fine. Okay. Again, as far as I'm concerned, we implement that in n squared time. Don't worry if I said anything different. Okay. Any questions? Okay. Let's now look at a couple of very, very simple problems that, if you think about them the right way, can be thought of as dynamic programming problems. Okay. And this is an example maybe of how you formulate the recurrence. Okay, let's see. Okay, let's say we are driving from New York to Florida. Here is New York. Here is Florida. Okay, you want to end up at Disneyland. Okay. And along the way, there are gas stations. And being a efficient planner, you would like to find the best set of gas stations to stop at between here and on your trip. Okay. And in particular, we'd like to minimize the time we need to stop. Okay. So we're going to assume that we have a car with a driving range of R miles, okay? We're going to assume that the ith gas station, G sub I, is located at mile M of I. Okay, so we know how many miles. This is M1. This is going to be M2. Okay, we know the distance, the mile marker for every gas station. How would we find the minimum number of what you call of places to stop? Can anyone give me an algorithm, a way of thinking about it, to find the shortest, fewest number of stops you need to make between here and Florida, given this data? Does anyone have an approach? Some of you should have an easy approach that happens to be right, although it doesn't happen to be dynamic programming. What would be a way of dealing with this? Any ideas? You see, do you understand what the problem is? Find the smallest number of gas stations to go, okay, to stop at in order for me to drive from New York to Florida. Okay, any ideas how to do this?
Keep adding mile markers until you reach a point where you can't add any more, and then you visit the gas station that you
okay, so you're
most
saying
recently.
You are proposing a greedy algorithm for this, right? You're saying start from item number 1, look at where R miles of driving range is from that, and you want to take the gas station that is closest to this, right? You want to empty the tank as much as possible before filling that up. Does everybody kind of see that? And then he's going to do it again. He's coming up with a greedy algorithm for this, right? That's R, and I'll let you get where you got to go, okay? That's a correct algorithm in this case, but I don't want you to think about it that way, okay? Can anybody think of a way to do this doing breadth first search? Let's think about it. Okay. Can anyone think of a way to solve this problem as a graph problem? Just to remind us of stuff that we know about. Okay. Any ideas? What if I build a graph, okay, where I add an edge between any two places that are within my distance of R of each other? I can get from here to here with an R, here to here with an R, here to here with an R, here to here with an R. Does everybody agree with that? If I now fill up my tank here, I can get from here to there. I can get from here to there, to there, to there. Does everybody kind of see this? I could build a graph where every pair of vertices that are within a driving distance of R, I have an edge between. Now, how would I use that graph to find the minimum number of hops I need to use from here to here? How would I do that? Is there anything we've done that smells at all like this? The path with the fewest edges, okay? How on earth could we find such a thing? Any ideas, or is this hopeless? How do you find the path with fewest edges from here to there? Somebody. Hopeless. Okay, there's no algorithm for this. Okay, is it possible? Can anybody conceive of an algorithm? I hear shortest path. Shortest path would work. Should we use Dijkstra's algorithm for this problem to find the shortest path? Okay, I'm hearing DFS. DFS is the wrong answer because that's depth first search. That has nothing to do with finding shortest path. What does have something to do with finding shortest path? BFS. Okay, now this is not hopeless anymore, right? Does everybody agree that breadth first, this is an unweighted graph. I can find the smallest hops by starting at BFS here until I discover that vertex. And that's going to be the fewest number of gas stations. Does everybody agree? Okay, let me now show you a dynamic programming way to do it. Okay, and this again is maybe not such a feat because you're saying, oh, I've already seen two other ways to do it. But what about this? In dynamic programming, I start by defining a function that will, what you call it, if I knew the answer would tell me what I want. Let's let G sub I be the minimum number of filling ups that I need to get to gas station I. Okay? If I knew this function, would this solve my problem? Okay, I want to drive from, I guess, my house in New York to my house, my mother's apartment in Florida. Okay, so I guess what I need is not just a graph with all the gas stations. The last quote unquote gas station, let's say, is my mother's house. Okay, and then this is gas station 1, 2, 3, 4. This is going to be, I'm going to consider my destination gas station N. If I knew how to compute the minimum number of fill-ups to get to every single point in the graph, on the line, every single station, I'm done. Now the question is, can I come up with a recurrence relation to compute this function? And I claim this recurrence relation does it. So I want you guys to look at this very carefully and look at this. What is the minimum number of filling stations to get to gas station I? Well, I claim it is the minimum over all J, okay, where all J less than I, where the mile marker from J minus the mile marker from I is less than R. What does this mean? This says, let's try all stations before, if this was station I, let's try all stations J that are within a distance of R of I. Does everybody see that? These are the possible previous stations. And what am I going to say? I want the answer for the number of hops to end up at station I is going to be the minimum over all possible previous stations of the number of hops of getting to I plus 1. Does everybody see that this recurrence relation does what I want? If you don't, this is a great question to ask. Okay? Why is it not less than or equal to R? Okay, fine, it's less than or equal. If you really want to run the risk of really emptying your gas tank, you can make it greater than or equal to R. So you're kind of coasting to this station. Okay? If you want to do that, it's less than or equal to R. Okay? Any questions about this? Do people see what this algorithm is doing? I'm going to start with what's the cost of getting to the first station? What's the how much many stops in gas, if assuming I'm starting with a full tank, how many stops do I have to make to get from my starting point to my starting point? I'm going to claim that 0, right? Or if you want to say maybe I'm starting at a gas station where I juice it, in which case I'd say my initial case would be 1. Do people see what this recurrence relation does and that it does the computation that I would like? Any questions about this? So what are we going to do? We're going to fill up our array G of 1 is going to have its boundary case of 0. Then I'm going to go through it and successively fill in this by checking all legal J before it. Once I know that, then I'm going to go fill this by checking all legal J before it. Okay. And I'm going to keep doing this until I get up to the last cell. That is the idea. Why do we have the +1? That's a good question. Why is that +1 there? Well, this is telling me where my last stop was. This recurrence relation is saying the cheapest way to end up at station I, gas station I, is one more fill up than it took to get to gas station I +1, my previous gas station. So I'm assuming if I'm going to stop at station I have to pay the cost of the stop. This is the cost of the stop. This is how many stops it took to get to that previous station. Okay. So if I knew that getting to J, I made a total of 3 stops. If I'm now going to then go and stop at station I, I'm going to be paying 3 + 1 stops. Any other questions about this recurrence? Are we assuming that I and J are, what do you mean, I ++ and J ++? I don't know what that means. Okay. So at each stop, you're checking what? Okay. At each stop, I'm going to fill my gas station. I'm going to fill my car. Okay. That's what I'm going to do at a stop. At the end after I have filled up my car, I now have the room to drive R miles again. This says, what is the cheapest way to get the fewest stops to get the ith station? Well, I'm going to have to stop at some previous station and make one more stop than it took to get to my previous stop. GJ is by definition the minimum possible number of fill-ups to get the station GI. So GJ would be minimum number of fill-ups to get the station J, and GI is going to be this thing. Okay. Again, I'm confused by the questions on the chat. Somebody with a voice is what I'd like to hear. Any questions if you don't get it? What is the running time of this algorithm? This is an algorithm to find the smallest number of hops to get from G1 to Gn. What is the running time of this algorithm? Can anybody tell me? Okay. Well, I count the running time of a dynamic programming by how many boxes am I filling times how much time does it take to fill each box. Okay. How many boxes do I have to fill? I'm going from gas station 1 to gas station N. So there are a total of N spots that I'm going to fill. And each one of these is doing a min where I'm going to look back at a bunch of gas stations. If my driving range R is extremely big, I might have to look back at all my gas stations or half my gas stations. To do this, I might have to look at order N possible things. I claim that it's N boxes times N time per box. Any questions about that? Any questions about where that comes from? And so in the worst case would occur if R was equal to N. The worst case would be for this running time algorithm would be if my driving range was such. Remember, R is a driving range. It's comparing miles, not N's, right? But if I was driving a fuel truck, okay, I would be able to get from here to Florida on one fill But in order for the algorithm to fill it out, there would be, by the time I got to this station, it's possible I would have chosen to fill it up at any one of the other things. So yeah, the bigger my capacity is, okay, it might be that I might be able to look back to theta n gas stations and get within there. Okay, so that's why I say it's going to be n times n, or n squared. Any questions? Okay. Okay, let's say that that's going to try one more of these things. Okay, what are the observations? Let's just remind us. It's n squared algorithm. We could have done it by BFS. This is sort of like a shortest path problem. In fact, it's a shortest path on an unweighted graph. And that's true for a lot of dynamic programming. But with the dynamic programming thing, there's all kinds of ways you can generalize this idea. And I'm not going to talk about them. You can look at some of the slides, but recognize that I could generalize this to what if I want to, what if the gas at different gas stations cost different amounts? What is the right place that what are the right gas stations I should stop if I want to make it cheap? Okay. So there's more that you can do here. Any questions about gas stations or anything like that? Okay. That said, let's now go back to the problem of the day. Okay. And this problem of the day is going to be pretty closely related to the dynamic programming algorithm I'm going to talk about today, later on, a very important thing called string edit distance. But I want us to think this thing through. So take a deep breath and let's think about this problem. We are given 3 strings of characters. There is a string X, okay, that is n characters long, a string Y that is m characters long, and a string Z that is n plus m characters long. We will claim that Z is a shuffle of X and Y. If Z can be formed by interleaving the characters, okay, such that the things are a left to right, okay, ordering of the 2 characters. So let's just make sure we understand it. This phrase, chocolyptes, I guess that's what it is how I pronounce it. Can this be made by interleaving the chocolate and the chips? Here's chocolate, here's chips. Is there a way to kind of embed the word chips in this, such that when you delete the letters of those chips, you get chocolate? Can anybody propose to me a place where the chips should be? Presumably the first letter of chips could be either the first C or the last C. Let's make it that. The last letter of chips could be a S, so that's got to be it. There's only one P, so that's there. Now I need an I. There's only one I guess I could take that. And if I do this, can I take either of these H's? If I take either of these H's, sorry about this. If I take either of these H's, does everybody see that if I take either of these H's, I would have spell out the word CHIPS? That's chips, right? Is it true that that I could take either of these H's, pull out chips, and then leave chocolate? Okay, they're saying no. If I take the first H, I will get chips. But now what's left is COC and not CHOC. Does everybody see that? So in order for me to get chocolate and chips, this has got to be CHOC. And now what's left is chocolate. Does everybody see that? So there is a way to interleave chocolate and chips. Is there a way to get a chocolate and a chips from this word? Can anybody argue to me that this word can't be constructed into chocolate and chips?
You can get the word chocolate, but the letters left over for chips are spelled CHISP.
Okay, you're saying that that if I grab a chocolate, you think that you can get a chocolate, but what's left won't be chips. Okay, I probably need a little bit of a proof of that. The proof that I think I like is that chips has to end with an S. Does everybody agree? And if it ends with this S, well, I can't get the P. I need the P before the S, and the P is after the S. Does everybody see that? So here there is no chocolate and chips, but the other word there is. Okay? Any questions? Now is the real point of all this. Can you give me an algorithm, okay, to tell if I give you a Z, an X string, a Y string, and a Z string? A Y string and a Z string. Tell me whether or not Z is a shuffle of X and Y. Okay? Does anybody have any idea how we would do this?
Yeah, so we would start off by creating an array, a Boolean array of the same size as Z. Obviously, we'd want to check to verify first before we go into the more meat of the algorithm, verify that the length of Z is equal to the length of X plus the length of Y.
So first of all, you're telling me something interesting here. You're telling me that the length of X plus the length of Y had better be the length of Z, or else we're doomed to failure. Does everybody agree? Okay. If I ask, is there a way to shuffle Skeena plus cat into supercalifragilisticexpialidocious? No chance, right? What else is there now? Keep going.
So then we just have a Boolean array of size Z. And what we can do is we can start off by going through Z once and then choose either X or Y. We'll have two, we're gonna have to go through the entirety of X and the entirety of Y. So it'll be two passes through Z. But what we're gonna do is we go through X and we start off at the first position in X, right? And for each letter in Z, if the letter at the index that we're currently at in X is equal to the letter that we're currently at in Z, then we mark the Boolean array as true, and we move to the next position in X and move to the next position in Z.
Okay.
And we
may or may not be saying this. Okay, so there's two things you could be saying. Okay, and one of them isn't right. Okay, and or one of them isn't efficient, and that's what I think you're saying. But let's just go through it and see if I'm right. You're saying, take a look at Z, which is the, the bigger of the words. And you're going to want us to look for one of these words, maybe the smallest one. Let's say X in particular. And you're going to say, well, if X is going to be in here, well, then I'm going to find the first letter of X, and I'm going to consider that. And that's now going to match the first letter of my word. Then I'm going to look in Z for the next letter of my word, and keep walking like this. Notice, though, that there can be a lot of choices for what the first letter is and what the second letter is. And it's not a simple read from right to left thing. Is this what you were trying to kind of suggest?
Well, couldn't we just assume that like the first occurrence of like, say with the chips and the whatever example, right?
Yeah.
Or chocolate too. Couldn't we assume that the first C could correspond to whatever word we're using as the other one.
Okay, so the first C, you're saying, if we have a world where the first string began with C and let's say it was cat and dog. If we see a C at the beginning of Z, does that have to belong to X, cat? Yes. But what's the nasty problem? What if I have two things that begin with let's say that it's cat and cog. Now, if Z begins with a C, which C should I use?
The first one?
The first one? The answer is no, because it turned out that Z began like this with CO. Okay? Does everybody see you can't make that decision of which C to use by just looking at the beginning? Because they both begin with C. And if Z began CO, then you'd better have taken the first C from Z. Does everybody kind of see that?
I have an idea for what
So
you're
there's
saying.
one big thing to notice here. This is complicated. There's lots of choices here. You might be saying, oh, I know, I'll do backtracking to find the right subset. Okay? And that would be a respectable thing. That's a recursive thing. That will get it right. But it will require an exponential search. That's a problem, right? Okay, now what's your idea?
I was thinking like, okay, so you can have a matrix of n by m, and you can essentially like the n would be like the word that's of length n, and same thing for m. And basically what you would do is you would start at the index n comma m, and you'd basically say, okay, we're gonna start from here and we need to we're gonna look at the first letter in Z, and we're gonna say, okay, is this letter part of either the last letter of the nth letter of the word that has n letters, or the mth letter of the word that has m letters. And if it's either one of those, then you would make it true, and then you would go in the direction.
This to me is, let's say the answer is maybe, but I'm confused now. Let me show you now how I think about this, because I want you to think about this as a dynamic programming thing. You may be, okay, but at the moment I'm confused. Let me tell you how I'm going to do it now, okay? I want to do it by dynamic programming. I start by defining a function, a Boolean function, it looks like they're telling me, that if I knew the answer to this, okay, I would have a winning solution. What if I have a function, let's call it S for shuffle, of I, J, K, which is going to be equal to true if and only if X from 1 dot 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 I and Y 1 to dot 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 J can be shuffled to Z 1 dot 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 I plus J, not I plus J, let's say K. Although I think the beans will be spilled soon. Does everybody see that if I could compute what this function is doing? S sub ijk is true if it's possible to shuffle the first I characters of X and the first J characters of Y into the first K characters of Z. Does everybody see that if I could compute this thing, this would solve my problem? I really want to know is what is S of length of X, comma, length of Y, comma, length of Z. Does everybody see that if I could find, I want this, if this is the question I'm being asked. Can all of X be and all of Y be shuffled to all of Z? if I could answer this for all the prefixes, this would give me my desired solution. Okay, how many people are with me here? If I could do this, this would answer my problem. Okay. And now, before I go and show you how to do it, could we use this idea to make for a simpler function? Simpler to me means less arguments to my recursive function. Can anybody see how to make this thing with fewer arguments and compute something that's still useful to me?
I was thinking, I mean, I'm not sure about this, but instead of using 2 arrays, you could use a matrix. But I mean,
First of all, I'm not saying 2 arrays, 3 arrays, matrix. I never said anything about it.
okay. Never mind.
Okay. I have a function. This is a function with arguments. If I knew how to write a program, an algorithm to compute this function, I would be done. Is there a simpler function that would do the same thing using one less argument?
Yeah, can we use say like I and K, and say that after subtracting the elements of I out of K, we get J, basically?
What you're saying is, I want to take your idea and do it slightly differently, but that was bad, right? What am I going to do to change it? What if I get rid of this K and I instead say that K over here equals I plus J? Does everybody see that what I really want to know is, can the first I characters of X and the first J characters of Y, can they be shuffled into the first I plus J characters of Z? If so, then what I really want to know under this function is, can the first X characters of this first string, which means the entire thing, plus the first Y characters of the second string, meaning the entire thing, be shuffled to the first I plus J characters of Z? So does everybody see that I now have a 2-parameter function where I used to have a 3-parameter function? Any questions? Okay. Now, can anyone give me a recurrence relation to compute what S, so S sub ij, just to remind us, is equal to true if and only if x sub 1 dot 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 to I plus y 1 dot 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 to j equals z, can be shuffled into z1 to dot 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 I plus j. That's what we're looking for. Can anyone give me a recurrence relation to compute this function? A recursive idea. Okay, you're saying, what is the basis cases? We could deal with basis cases. I usually deal with basis cases later. But can anyone give me some values of this function that are pretty easy to compute?
If we're looking for the recurrence relation, we're looking at S of, say, like I minus 1.
Okay. We'd like this to depend upon S of I minus 1j, or maybe S of I comma j minus 1. So my question is, can you tell me under what conditions can we do this shuffling? Any ideas? Let me show you my way of doing it. Let me think about this for a moment. I claim that you can do this if, kabunk, kabunk, z of I plus j is equal to x sub I and s sub I minus 1, comma, j. Okay, look at this. One way I could do it is, suppose the last character of z was equal to the last character of I. Then I could put, then I could that tells me I now know where the last character of z comes from. If I can shuffle all of the first string of x except that character, plus all of the second string, if that can be properly shuffled for z, and the last character matches, then this gives me a way to realize that. Does everybody kind of see that? Not seeing everybody. Does anybody see this? Either, if I'm going to shuffle the first two strings to get z, the last character of z is either the last character of the first string, x, or it's the last character of the second string. This gives me a way to tell if it's the last character of the second string, right? Okay. How would I tell, I'm going to now say or, if anyone understands what I'm saying, how do I deal with it being the last character of the second string? What would be the way that would work? Can anybody see this?
zi plus j is equal to yi plus s I and then j minus 1.
Wait, y j, not y
Oh, yeah, right, j plus
and
s
what?
plus s I j minus 1.
Does everybody see that this is my recursive algorithm? I can do the shuffle of the entire strings up to I and j if and only if I can match the last character of the string to x, and I can realize it without that. Okay, all the prefixes of those strings, or I can match it to the what you call it, last character of y, and realize the prefixes of the remaining strings. Does everybody kind of see that this condition does the test that I want recursively? It is recursive because notice here's S, here is S, and here is S. Okay? Any questions about this? Some people are complaining, give me a basis case. Okay, can anyone give me a basis case? I do need a basis case for my recurrence. A basis case for a recurrence is something so simple that I know that it has to be right. What do I know the answer of? ij0. What is S of 0, 0?
True.
Is it true that I can match the, remember this is a Boolean thing, right? It's true. Can I shuffle the first 0 characters of x and 0 characters of y to make the first 0 characters of z? Can I do it? Somebody yell. I'm hearing nodding, but do I see yell? It's got to be true, right? So this gives me a basis case, okay? And I believe it's a good enough basis case to do what I want, okay? Although, what about if I give you some other basis cases? Under what condition is, what is S of I comma 0 equal to?
Wouldn't it be true because you can only put that one letter in the spot?
Well, it says, what can I shuffle the first I characters of X and 0 characters of Y into Z, the first I characters of Z? Is that always true? Not necessarily. Okay. Suppose that my Z, my X is cat and my Z is dog. Okay. Can I put the first 3 letters of X into the first 3 letters of Z? No. So under what condition is X of S of 0, I comma 0 true? Basically, this is true if and only if X sub 1 comma I up to I is equal to Z from 1 to I, right? Any questions about that? Okay. Again, I'm not seeing understanding the questions here. Okay.
Can I ask a quick question on that
Yeah.
expression there?
Yeah. Which question? The main recurrence or the
The last thing that you just did. Would it be equivalent to say like the ith character of Z is equal to the ith character of X and S of I minus 1 at 0 is true? Kind of the first term in the OR that we had above.
Yeah, it's kind of the first term in the OR. I'm not sure I even need this basis case, to be perfectly honest with you. I'd have to think about that a little bit more. Okay. But you're right. This is basically this kind of a case. Basically, what's true is the way to fill in this would give me a way to fill in kind of a row of a matrix here. Because basically there's going to be a certain point in which the prefix of Z equals the prefix of I. All of these are going to, of X, these are all going to be true, and then it's all going to be false. Okay? So yeah, so there is these kind of basis cases. But do people see what this recurrence is trying to do? Or does this look like it's completely from Mars? Any question? Mars, okay? Any questions? Okay.
Can you just go through it again, like how you structure the
Okay, so
solution?
what am I doing here? That sounded like Mars music actually in the background. Okay. What does this say? I am trying to compute a function. I have defined a function S of ij, which is going to be true if and only if the first I characters of X and the first J characters of Y can be shuffled into the first I plus J characters of Z. For certain X, Y, and Z, and I and J's, the answer is going to be true. And for certain X, Y, Z's, I's, and J's, it's going to be false. How can I tell what that value is? Well, I can shuffle the first I characters of X and the first J characters of Y into Z if and only if the last character of X matches the I plus Jth character of Z, and that means I can realize the first I plus J minus 1 characters of Z by matching everything in X except the last character, that was taken care of here, plus all of Y. Okay? Do you see what the reasoning here is? A legal way to do the shuffling will exist if the last character of X equals the last character of Z, and there's a way to shuffle everything except those last characters. That's this. Another legal way to do it is if the last character of Y matches the last character of Z. And there was a way of shuffling all of X and all of Y minus that last character. So either I could do it this way, or I could do it this way, or I could do it both ways. The or doesn't care. Or if I can't do it either of these ways, then that means there's no possible way to do the shuffling and the value would be false. Any questions about that?
Sorry, one more quick clarification. Is the plus a Boolean and or an addition?
This should be an and, right? You're telling me my handwriting isn't so good? Okay, horrified by that. These are Boolean things, right? So that's got to be an and. Does that make you happier?
Yes, thank you.
Last character and that, okay? Or the last character and that. That's what it's telling me, right? Any questions about this? Okay. How many people sort of see where the recurrence comes from? You may say, my God, how could you conceive such a thing? But you see where this thing is coming from now? Any questions? Now, the acid test. What is the running time of this algorithm? Suppose the length of the first string is n and the second string is m. What is the running time of this algorithm? Okay. Now, people are aggressively throwing out things. Okay. How do I do this? I want to know it is the number of boxes times the time per box, right? How many boxes will I need to store in my matrix?
N times m.
N times m boxes, right? Does everybody kind of see that? This first argument is going to go from 1 to n. The second argument goes from 1 to m. N times m boxes. How much time does it take to fill up each box using this thing? What is the running time to implement this recurrence, to fill in a box?
Constant time.
Constant time.
We just need to check the last letters twice.
Is this character equal to that character? That's looking up two characters and positions in arrays. Are they the same? Constant time. This is reading something out from that table that I built. That's constant time. Anding two things together, constant time. I now look this character and compare it to that character, constant time. I look this thing up, I and it, constant time. I now have two things and I or it. Does everybody see that this is going to take constant time per box? This is an n times m algorithm. Any question about it? Okay. I've spent more time on this than I normally do, but I like this. If people get it, this is a great thing. Okay. And if you don't get it, this is a thing to look at and to figure out why it is. You need to understand why the recurrence works, and you need to understand why it is n times m. Okay, which is namely boxes, number of boxes times the time per box. Any questions about that?
Yeah, I had a question.
Yeah, what about?
In this case, you're assuming that if you ever compute a value, you would store the value, right?
Yeah.
But what happens if you don't store the value? Would that
If
change
you
the
don't
runtime?
store a value, then your program did something weird. What are you doing? You're in control of your program. Your program doesn't just do things by itself, right? You are going to build a matrix that is n by m, and each one of these cells is going to store a value. We kind of agreed, if you want, that this value over here should be equal to 0. I mean, it's false. Actually, I said it was true. This should be true, excuse me. In fact, if we wanted to work at this, we could actually initialize. It might be that along by my extra initialization condition, which may not really be necessary, for a certain range of x, it's going to match the prefix of this will match the prefix of z. Then once it mismatches, it's not going to ever match again. On the other side, again, the prefixes may match or up at some point will stop matching. Then what do I got to do? I am then going to fill this table in the order of such that the items I need are there. If this cell here, this is going to be my I, this is going to be my J. What cells does I and J need? I think that the cells that I need are going to be, and I'm going to try another color, this cell and this cell. If either one of these is true and the character matches, then this is going to be true. For this one, I'm going to need to use this value and that value. Okay, because again, to compute ij, I'm going to do I, j minus 1, and I minus 1j. So I'm going to fill my table in. Yuck, I know this is. Okay, I'm going to fill my table in, going down rows, knowing that I need that. So long as I have this element and this element, I can fill in this element. Okay, any questions about that? Think about it and keep playing. Okay, any burning questions? Okay, so we didn't get very far so far, but if you understood that, that's a good thing. And if not, I think it's a good example to look at. That's another, okay. What do I really want to talk about for today's lecture? I know maybe we're a little bit late to start today's lecture, but what I want to talk about is a very important problem, one of the most famous dynamic programming algorithms, one that's truly useful. You may be thinking, you know, I don't really want to shuffle chocolate and chips, and that I can respect. But there's a related problem that is very, very valuable, which is how do I, deal with matching strings when there are spelling errors? Does anybody see the spelling error in this sentence? Where is there a spelling error? Any of you guys good spellers? Apparently not. Okay, anyone see the spelling error? Okay, misspell. I believe that misspell has 2 S's. Okay, so I misspelled misspell. Okay, but the question really is, if I want to compare strings, I think you guys by now could pretty easily, given one string and another string, tell whether they're the same. Just compare every character one after another. We did something earlier in the semester where you guys had an algorithm for comparing whether one string is a substring of the other string. Remember, we had the short string, we kind of slid over the first string and we compared all the characters. And if they all matched, that's fine. If not, we slid it over one position and did it again. But what if I want to find an approximate string match? Namely, I want to figure out what's the smallest number of changes to convert one string into another. Okay? So how many changes does it take to convert skina into skiing? Is that how you spell skiing? Is skiing 1 I or 2 I's? Okay.
2.
2. Okay, good. How would I go and convert skina into skiing? How many changes do I need to make? The changes I'm allowed to do is I am allowed to change one character from one letter to another. So I could change shot to spot in one substitution. Does everybody see that? I'm allowed to insert a character, okay? A go to, so I could, how many changes do I need to make turn a go into a gog? I claim if I stick a G at the end, a go equals a gog. One change will do that. How many changes do I need to make to turn hour into hour? Well, the time into the possessive, okay, one deletion will do it. How many changes does it take to turn Skina into skiing? Actually, I think I'd rather display this a little differently. I'm going to stack them up next to each other just to see Skina and skiing. What is the number of changes that you would make? I claim in this case it would be 2 substitutions. Does everybody see that? If I make 2 substitutions, I can turn Skina into skiing. Does everybody see that? What if we want to turn Skina into the misspelling of skiing? What is the minimum number of changes it takes to do this?
Still 2.
Still 2, but what kind of changes would I make?
Substitution on G for A and then deletion of E.
So you would say match, 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 delete, match, substitute, right? So we want to try to find what are the edit distance problem is find the cheapest sequence of changes to convert one string into another. Okay? Any questions? Can anyone think of why I might want to convert solve an edit distance problem? Find the smallest number of changes between 2 documents?
This might help with, say, like an auto-correcting algorithm.
Like a what?
Like
Autocorrect.
auto-correcting.
So it's sort of like you type some random string and you want it to figure out what's the smallest number of changes I need to turn it to a legal word in English. That would be fair, right? Okay. Let's say I want to figure out, I see I have my solution to to a homework. Here's my homework answer key. And here is your, no doubt, plagiarized solution to it. If I want to find what is the smallest number of changes, how would I tell whether you plagiarized my homework? Well, if I could figure out what's the smallest number of changes you could make to your homework to turn it into my answer key, or equivalently to turn my answer key into your homework. If I could prove that there were a small number of changes that would do it, then you probably plagiarized. Does everybody kind of get that? Okay, so I'm going to be interested in edit distance. Okay, any questions? Okay, let me show you a recursive algorithm for edit distance. Okay, and it's sort of a little bit like my chocolate chips algorithm, in that I'm going to be wanting to do a recursive algorithm where I'm going to figure out what must I do with the last character in the string. Okay, I am claiming that if I want to edit S into T, okay, there are 3 possible things that can happen at the end. One is maybe this string ends in let's say this string ends in an E and this string ends in an A. Maybe I am going to want to do a substitution, turn the E into an A. Does everybody see that I'm allowed to do a substitution. I would do a substitution if the last two characters don't equal. Or maybe I will delete the first character from X, the last character from X. Or I will choose to insert an A into X as the last character of X, so that it now matches the last character of T. Those are the only three things that can happen. Actually, well, conceptually, there's four things that can happen. Either if the last two characters, the last character of each string is the same, maybe I'm going to choose to match them. If not, I may choose to substitute them, or I may delete one, or I may choose to insert one. Those are the only four possibilities. Does everybody see that in any alignment of the two strings, that's the only things that can happen at the end? What is my recursive algorithm? Let's let d sub ij be the minimum number of changes to convert the first I characters of string S into the first j characters of string T. Let's say I want to define this recursive function. My claim is that dij is going to be the minimum. In the best possible alignment, something's going to have to happen at the end. It's either going to end on a match, a substitution, an insertion, or a deletion. I claim that what I want is the min over four possibilities. If the last two characters, the last character of each string is the same, I could match them and pay a cost of what it takes to edit the first I minus 1 characters of S into the first J minus 1 characters of T. That's one choice. If the last characters differ, I could pay the same price, what it costs to edit the prefixes to each other, plus 1 to pay for this substitution. Does everybody kind of see that? If I'm editing, how do I edit A into B? Well, I could pay 0 plus the cost of that substitution. Or I might choose to do an insertion. Okay? If I do an insertion at the end of my first string, that's really going to be telling me the only reason I do that insertion is to match the last string of the other character of the other string. I pay 1 for doing the insertion, and what's left is I still have I characters of the top string, but now j minus 1 unmatched characters of the bottom string. Or I could choose to delete a character from the bottom string. Okay? Actually, or delete a character from the top string. If I choose to delete it, okay, I pay 1 for that deletion. And I now have the problem of matching everything on the top except the last character to everything on the bottom. The cheapest way to edit the entire strings together is the cheapest of these four possibilities. And this gives me a recursive algorithm because d of ij depends upon smaller values of d. Any questions about this recurrence? Do people see why this recurrence is correct? Okay, you may not see it's a recursive algorithm. Something has to happen on the other side. These are all the possibilities. The cheapest way is going to be the way that costs the least. This is going to be the cheapest way for ending in all of the four possibilities. Any questions? Okay, I want you to think about this think about why this recurrence is correct. And then I will show you how to implement it next time in dynamic programming. Any questions about it? This is a good thing. Understand why is this correct next time. If you believe that, if you'll do that, I'll let you go and say have a good weekend.